Welcome to BKW Physics. I'm Mr. McConnelly, and today we're going to talk about magnetism. And the way I want to start this off is a little discussion. How many people have seen the northern lights, the aurora borealis? Pretty cool, isn't it? How's that work? Let's relate to this somehow. Magic. How's that work? It is magic.
Physics magic.
Physics magic. Yeah, magnetism causes it. Very good. Very good. Well, what happens is, and people always had theories about this for hundreds of years, but what really happens is that solar wind blows these charged particles into our Earth's atmosphere. Now, once it enters our Earth's atmosphere, we have a shield of magnetism, the north-south around our Earth. And so that magnetism starts affecting the different things, the oxygen, nitrogen, and whatnot, and excites the electrons. And those electrons start jumping and start emitting visible light. So as that solar wind blows particles in, you're getting all different types of elements excited, and then you start seeing greens and reds glowing in the sky as the electrons are jumping. And so it's actually caused by magnetism and charge. And there's a relation between the two, which we're not going to talk about today, but we will get back to. The two things are very, very closely related. So, more simply though, because that's kind of a complex thing, more simply, how do permanent magnets work? If you take this chunk of magnetic material, and you take this chunk of non-magnetic material, how do they differ? Well, inside of them, you have these domains. And if it's magnetic, generally speaking, now I'm drawing these arrows kind of all pointing to the right. I don't want them exactly pointing to the right because that would be unrealistic, but kind of everything's pointing to the right. So you can think of these ferromagnetic pieces. Ferro, iron. Ferromagnetic pieces as all kind of pointing the same direction, as opposed to a non-metallic, magnetic thing, I can't speak. A non-magnetic thing, you kind of have random direction. They're kind of just pointing haphazardly each direction. But when they start aligning themselves, now everything's pointing in one direction. This is going to be magnetic. Okay? And if you just take a chunk of metal, like a bar magnet, and you heat it up until it's liquid form, so you got molten metal, and then you expose it to a north and a south while it's liquid, what happens to the ferromagnetic pieces? Well, they kind of align themselves like this because they're freely able to move around because it's liquid, and now they align themselves. Now you cool it off, and what are you left with? You're left with a magnet, and those pieces are stuck. You can almost think about it as what you learned in earth science with the mid-Atlantic ridge of the Atlantic Ocean. As the molten magma comes up and the Earth's magnetic field, it aligns the ferromagnetic pieces. And that's how they know the Earth's magnetic field used to be the other direction. North used to be in the south, and south used to be in the north. Because they can look at the ferromagnetic pieces and see how they're all lined up. Okay, moving on. When you have permanent magnets, let's just draw another bar magnet. When you have a bar magnet like this, there's going to be a magnetic flux. And flux basically means the strength of the magnetic field. Now notice the way I'm drawing these arrows. I'm drawing these arrows, and notice all the arrows are pointing towards the south, or north to south. Remember when we drew electric fields? We had a certain way we pointed the arrows? Same with magnetic fields. Magnetic field arrows, flux arrows, they always point towards the South Pole, or north to south, however you want to say that. But the magnetism is always shown that way. And the other key factor here is my circle right here. See how these lines are close together here? The relative closeness of the magnetic field lines indicates the strength. So this is stronger. Whereas, if you get out here, the spacing is, we'll say, far apart, so this is weak. And it kind of only makes sense. Where do you think a magnet is strongest? Well, when you're close to the magnet, A, and when you're near the, what are these called? Two ends? Poles. So if you're near the poles and you're near the magnet itself, it's stronger. The flux density is greater. Flux density, how close? Okay, flux density is greater, stronger as you get closer. That makes sense. One more thing that confuses some students is if you put a compass, a north-south compass, that's what the purpose is. They're able to tell you north and south. Which way would the compass point right now? What do compasses always find for you? They find magnetic north. So this compass would go like that, wouldn't it? It would align itself with the magnetic field. So it's aligning itself with the magnetic field. So in other words, if I put one up here, how's it going to align itself with the magnetic field? But it's going to point itself at the North Pole. That being said, the little arrow I've drawn on the compass, do you understand? You know, these are, you know what a compass is, right? I don't need to show you one. So these are just tiny compasses that I'm placing near a magnet so you can see which way they're pointing. Which end is the arrow end of the compass then, in terms of a magnet? If it's attracted to the north, it must be a, yeah, that's what confuses people. This is a south, and this is a north. If you're talking about the little needle as being a magnet of its own, okay? The other way you can think of it is this, is if you had this bar magnet, and then you took another magnet and you dangled it by a string here, so you got a string holding up another bar magnet, how would that bar magnet arrange itself? Just like that, okay? So that is what you need to think of when you place the compass in a magnetic field. The other thing we gotta talk about real quickly is what are the units for magnetism? Well, if you've been to Niagara Falls, you saw a statue of Nikola Tesla, and the units are Tesla. And Tesla is abbreviated with a capital T. It's equivalent to a Weber per meter squared, but normally we're talking Teslas. Okay, how many Teslas of magnetism do you have? Again, if you're close to the magnet, and if the lines are close together, the magnetic field lines, you have a higher number of Teslas than if you're far away. And certain magnets are able to produce much more in terms of Teslas. Have you heard of neodymium magnets? Neodymium magnets, usually when you buy them, they're really little compact magnets, and they have quite strong. I'll show you one when the video is done. They're quite impressive. Well, I guess to end this, let's do a quick little demo, and I'll walk right over to the video in a second. I have here some goopy liquid, and in this goopy liquid is some iron filings, and I have some magnets, okay? So what I can do is I can shake it up so the iron filings are all dispersed there, and then hold the magnets in here, and I'll kind of walk around, show the video first. Am I on the screen well here? Closer? I can see that, good. So you can see that all the iron filings are arranging themselves, or they're aligning themselves with the actual magnetic field or the flux lines. So for today, that's physics.